We're going to go over some preliminaries for abstract algebra, and let's remind ourselves of some notation. The n, that sort of special n that looks sort of like this, represents the set of natural numbers. And z, that sort of special looking z, represents the set of integers. And q represents rational numbers. And that's numbers of the form, like, say, n over n, let's say, such that m and n are integers. So rational numbers, remember, rational kind of means ratio, so it means fractions of integers. Now, of course, this would include whole numbers, because whole numbers are fractions of integers, like 8 can be thought of as 8 over 1, etc. So Q is rational numbers. And then R is all real numbers. And usually R minus Q, or sometimes written as sort of like in set notation, like this. You can think of this as like the reals taking away the rationals. This represents irrational numbers. And so keep these in mind when we're working with. Of course, irrational numbers are numbers that cannot be represented as a fraction or a ratio. Like the most well-known ones, of course, are the square root of 2 and pi. They cannot be represented as a fraction or ratio of two whole numbers or two integers. Some other things to remember is, say, addition. Mod n, let's say. And so some examples would be maybe addition mod 7. What that means is, so let's say you're taking two numbers, let's say 4 plus 12 gives you 16, but then you divide 16 by 7, and that gives you what, 2 plus a remainder of 2. Because if you divide it by 7, you get 2, and then and your remainder is 2. Or if you have something like this, 14 plus 13 is 27. 27 divided by 7. That goes in 3 times. And then the remainder is 6. Now for negative numbers, let's say if you have something like negative 12, let's do something like this. Negative 12 minus 3 is minus 15. Minus 15 divided by 7. Now in this case, what you're going to have is this will be, say, negative 2 plus a remainder of this time. It will be what? Minus 1. And then now for negative numbers, and you have to add this 7, which is equal to 6, like this. So in other words, what this is all getting to, like these numbers here, so like over here, let me just rewrite these in a different way. So what we're saying here, like saying this first line here for 16, 16 is equal to, and sometimes they'll put like a third bar to emphasize this. 16 is equal to 2 mod 7. Because whenever you divide 16 by 7, you get 2, and the remainder is 2. So they say that 16 is equal to or congruent to, sometimes they might say congruent to 2 mod 7. Or over here for 27, 27 we found is equal to 3 plus 6. Once again, focusing on this remainder. This is 6 mod 7. And then for negative 15, that's equal to or congruent to, like I said, when we do this, you have to add the 7 for negative numbers, and that's going to be equal to 6 mod 7. Now, we could have done all this with like a wheel or a circle. So let's say for mod 7, which you do, you make a circle, say start at 0, and you have maybe 1, 2, 3, 4, 5, 6. You always stop short of 7. In other words, you always stop short of whatever you would have the mod here. So it's 0 to 6, like this. And now let's try each of these. Let's count in this direction, and you can write them, like say in this case, I wrote them clockwise. So if we count in a clockwise direction, 16, let's start at 0 and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We ended up at 2, just like we got over here. Or for 27, let's start at 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So I started at 0, counted to 27, and and landed on 6 over here. That's the same thing we got here. Now for negative 15, we just go in the opposite direction. Start at 0 and go in the opposite direction. And you don't have to add anything like we did when we divided this out. So let's go in this direction again. Since it's negative, go this way and start at 0, count to 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Once again, we ended up at 6. So that's modulo arithmetic. Again, you always, when you make a wheel like this, you always go from 0 to like n minus 1. In this case, 7, we're doing things mod 7, so we went from 1 to 6 like this. And of course, there would be no 7 here, because when we say divide 7 by 7, we get 1, but the remainder is 0. So you'll never have a remainder of 7. So we'll go from 1 to 6. And so let's look at a set that's closely related to what we're doing here. Let's consider the set, say, Z5. And now we're going to kind of keep this idea of modulo arithmetic in mind, because when you have a set like this, you'll do that modulo arithmetic. So Z5 consists of 0, 1, 2, 3, 4. Once again, you stop short. You stop short of whatever you have here. So when you have something like this, you end up using mod 5 arithmetic. That sort of comes with the territory when you have something like this. So, and this will work, of course, for any n. So for any n, you'll have 0, 1, 2, 3, 4, 5, on and on up to n minus 1, because you'll stop short of whatever this value is. So once again, if you're, let me do an example. Say if you do, let's do Z5, something pretty manageable. So we'll have, let's say if we take 2 times 4, that's going to give us 8. But of course, we want to find out what that is mod 5. And so we'll take the 8 divided by 5. That gives 1, and then the remainder is 3. So this is going to be equal to or congruent to 3 mod 5. Whatever number is here, that's going to be your modular, the mod. And so again, you could do it with a wheel. Like this. So here we had 8. So count 8. 1, 2, 3, 4, 5, 6, 7, 8. We landed on 3, which is what we had here. Or if you have like 4 plus 3, that gives you 7. And that's going to be congruent or equal to, so we take our 5, divide by 7. That gives us 1 with a remainder of 2. Again, write down your remainder. So it's 2 mod 5. Now, sometimes they'll put like a little number down here instead. So let's say if you have maybe something like this, let's say you have 4 times 3, which is 12. If you divide that by 5, that'll give you 2 with a remainder of 2. And so sometimes they'll put like a little 5 right after the equal sign or the congruent sign. Sometimes you'll see that notation. And as I mentioned before, if you get a negative number, you have to add to it. Now, in this case here, there's no negative, so we won't have to. Though, of course, if you have, you could subtract in some cases, depending on what you're doing. So if you have 1 minus 4, that's equal to minus 3. So if you divide that by 5, well, of course, actually, in this case, that is the remainder because it can't be divided by 5. 5 can't go into 1, so this is the remainder. But when we're doing mod arithmetic, we always have to add the 5, whatever this n is, to our number, which gives us 2. So again, whenever you have a negative, as usual, you divide it by, try to divide by 5. In this case, it 5 didn't go into this at all. So it was actually, this is the remainder. Again, whatever, if it's a negative remainder, you always add the mod number, which is 2, and that's going to be our 2 mod 5. So now also it on the wheel, if you were trying to find what -3 is mod 5, again, start at 0 and go 3 in the negative direction, in this case in the counterclockwise direction. 1, 2, 3, we landed on 2 over here, which is the same thing we got here. And one other thing to remember would be, say, complex numbers. So let's say if you have, remember, I is defined as equal to the square root of -1. And then, of course, I squared would be equal to -1. And also, if you think of, like, say, 1 over I, that's going to be equal to, let's say if we multiply the numerator and denominator by I, we're going to have I over I squared, which is equal to I over -1, which is equal to minus I. So 1 over I is equal to minus I. And also for some notation, the upside down V like this, or actually looks like it really an upside down A, means for all. And the backward E means there exists and this E like this means in, and like this means not in. So usually these have to do with sets. So like, for example, you might say A is in the set B, or you might say that A is not in the set B.